Okay, so I'm going to have you guys work on this example next. Okay, so I want you to pause the video, see if you guys can work this through all the way from start to end. Okay, so the directions here say to let f of x be equal to x raised to the 2/3 power, where 0.8 is less than or equal to x, which is less than or equal to 1.2. Part A asks you to find the third degree Taylor polynomial centered at x is equal to 1. And then part B says to use Taylor's inequality to estimate the accuracy of the approximation for f of x, which is equal to t sub 3 of x in the given interval. Okay, so let's go ahead and do part A here. So part A asks us to find the third degree Taylor polynomial centered at a is equal to 1. Okay, so we're going to take the function value, f of x, which is x to the 2/3 power, and then we're going to take out to the third derivative. Now, I'm going to go out to the fourth derivative because we're going to need to figure out the fourth derivative for part B in this problem. Okay, so f prime of x is going to be 2/3 x to the negative 1/3 power. F double prime will be negative 2/9 x to the negative 4/3 power. F triple prime will be 8/27 x raised to the negative 7/3 power. And then I'm going to find the fourth derivative again. I don't need it for part A, but I will need it for part B. So I'll do this in a different color. So the fourth derivative is going to wind up becoming negative 56/81 times x raised to the negative 10/3 power. Okay, and then what we're going to do is we're going to evaluate f prime, f double prime, f triple prime at 1, because that's going to give us our coefficients for the Taylor polynomial. So f of 1 is going to be 1, f prime of 1 is 2/3, f double prime of 1 is negative 2/9, f triple prime of 1 is going to be 8/27. Okay, so if we want the third degree Taylor polynomial, so t sub 3 of x, that is going to be equal to f of 1, which is 1, plus f prime of 1 times x minus 1, plus the next term, which would be f double prime of 1, which is negative 2/9 over 2 factorial times x minus 1 squared. And the next term would be f triple prime of 1, which is 8/27 divided by 3 factorial times x minus 1 cubed. Okay, and if I just go and simplify this really quick, so t sub 3 of x is going to be 1 plus 2/3 times x minus 1. I'm going to change that sign to minus. So 2/9 divided by 2 factorial is 1/9 times x minus 1 squared, plus 8/27 divided by 3 factorial. That's going to wind up simplifying to 4/81 times x minus 1 cubed. Okay, so that right there is part A. That is our third degree Taylor polynomial. Okay, and then part B says to use Taylor's inequality to estimate the accuracy of the approximation in the given interval. So basically what we're trying to do is find if we're going to use the Taylor polynomial, that third degree Taylor polynomial, to estimate the function value, what is going to be the maximum error on that interval from 0.8 to 1.2? Okay, so for part B, if we want to calculate the absolute value of r sub 3 of x, that is going to be less than or equal to m over 3 plus 1 factorial, so that's 4 factorial. Now, if our Taylor polynomial is centered at 1, like the maximum distance from where it's centered to a point on this interval, like the furthest distance from the centered point to a point on the interval is going to be the distance from either 1 to 1.2 or 1 to 0.8. Both of those distances there are 0.2. Okay, so we're going to take 0.2 and raise it to the 4th power. Again, we're trying to maximize, like calculate what the maximum error is going to be. Okay, so what we want to do to calculate m is, let's go back up here. So we said that when we take the absolute value of the n plus 1 derivative, we want that to be less than or equal to m. So we want m to be the maximum value of the absolute value of the n plus 1 derivative. Okay, so if I take the absolute value of the 4th derivative, that is going to be 56 over 81 times x raised to the 10⁻³ power. Okay, so if I want to maximize the value of that on this given interval here, I want to think to myself, what value on that interval can I plug in the place of x in order to make this expression right here as big as possible? And because that x raised to the 10⁻³ power is in our denominator, the smaller our denominator is, the bigger our fraction is going to be. So the biggest I can make that 4th derivative is by plugging the smallest number in the interval in the place of x. So we're going to get 56 over 81. The smallest value for x on the interval from 0.8 to 1.2 is 0.8 raised to the 10⁻³ power. Okay, so that's going to make the absolute value of r sub 3 of x less than or equal to m, which is 56 over 81 times 0.8 raised to the 10⁻³ power, divided by 4 factorial times 0.2 raised to the 4th power. So when you compute the value of all of that stuff, you're going to get the maximum error is less than or equal to approximately 0.00009697. Okay, so using the Taylor polynomial to like estimate the value of a function, like that estimation is a pretty good one for us, because the maximum error is just 0.00009697. All right, let's do one more example with this. Okay, so with this example here, we're going to be using Taylor series and Maclaurin series to approximate a definite integral to a desired accuracy. All right, so again, with this example, we're going to be using a Taylor series or a Maclaurin series to approximate a definite integral to a desired accuracy. Okay, and the directions for this example here ask us to approximate the integral from 0 to 1 of x times the cosine of x cubed, which we're integrating with respect to x, to within 3 decimal places. And I think this is a fantastic problem that utilizes so much of what we've talked about in the second half of chapter 11. Okay, really good problem, like tying multiple ideas and multiple concepts together. Okay, so first things first, like when I look at this integral here, like we don't have a technique at our disposal to like evaluate this integral by hand. Like we can't do u substitution. We're not going to be able to do integration by parts. This is not a like trigonometric integral that we can work with. So we don't have like an integration technique that we can use to like find the exact value of this integral here. Okay, so let's take some of the things that we've discussed in the second half of chapter 11 to work this through. Okay, so for starters, let's say we take the cosine function, okay, and we know that the max series for cosine is going to be the sum from 0 to infinity of -1 raised to the n power times x raised to the 2n power over 2n quantity factorial. Okay, so what I'm going to do is I'm going to take that function and also take that Maclaurin series, and we're going to manipulate both to where they look like this function here that we are trying to integrate. Okay, so if we want to take x times the cosine of x cubed, that's going to be x times the sum from 0 to infinity of -1 raised to the n power. Then we're going to plug x cubed in the place of x in our summation formula. So that's going to be x cubed raised to the 2n power over 2n quantity factorial. Okay, so I'm going to do a couple of things to simplify this. So number one, I am going to take x cubed raised to the 2n power. Because I have a power raised to a power, I'm going to multiply the exponents. So that's going to make x raised to the 6n power. And then because we're distributing x across every single term in that summation, I can work that factor of x inside of the summation formula. Okay, which means I can write that formula now as -1 raised to the n power times x raised to the 6n plus 1 power over 2n quantity factorial. Okay, so if we want to take then the integral from 0 to 1 of x times the cosine of x cubed, then what I'm going to do is I'm going to take the integral from 0 to 1. I'm going to replace that function x times the cosine of x cubed with its Maclaurin series, okay, which is going to be the sum from 0 to infinity of -1 to the n times x raised to the 6n plus 1 power over 2n quantity factorial, which we are integrating with respect to x. Okay, so this is different. This is the first time we've dealt with a definite integral with a summation formula inside of it. Okay, so all we're going to do here is we're going to find the antiderivative of that summation formula. We're not going to add a constant c here, okay, because we are taking a definite integral. All right, so when we integrate this summation formula, we're going to get -1 raised to the n power. X raised to the, we're going to add 1 to the exponent, so that's going to be x raised to the 6n plus 2 power. And then on bottom, we are going to have 6n plus 2 times the quantity 2n factorial. And then we are going to evaluate that sum at 1 and at 0. Okay, so when we plug 1 in the place of x, we're going to get the sum from 0 to infinity of -1 raised to the n power over 6n plus 2 times 2n quantity factorial minus, when we plug 0 in the place of x, we're going to get negative 1 raised to the n power times 0 raised to the 6n plus 2 power. That's going to be 0, which is going to make this whole thing here become 0. Okay? Which means that I can rewrite that integral then just as the sum from 0 to infinity of negative 1 raised to the n power over the quantity 6n plus 2 times 2n quantity factorial. Now, when we look at that summation, like that is going to be an alternating series. So if we want this to be accurate to within 3 decimal places, then we want to list the first few terms of the series until we get a fraction that is smaller than, if we want to be accurate out to 3 decimal places, that's tenths, hundredths, thousandths. We keep listing terms until our first neglected term is smaller than 1 over 1,000. Okay? All right, so let's list the first few terms of this. So when I plug 0 in, we get negative 1 to the 0 power, which is 1, over 6 times 0 plus 2. So that's going to be 2 times 0 factorial. 0 factorial is 1. So that first term becomes 1/2. Let's do the n is equal to 1 term. So we get negative 1 to the first power, which is negative 1 over. When we plug 1 in the place of n, we get 6 times 1, which is 6, plus 2 is 8, times 2 factorial, which is 2. 8 times 2 is 16. The next term we get by plugging 2 in the place of n. So that's negative 1 squared, which is positive 1, over 6 times 2, which is 12, plus 2 is 14, times 2 times 2, which, 2 times 2, which is 4 factorial. And 14 times 4 factorial is 336. Again, that's still not smaller than 1 over 1,000, so we have to keep going. So our next term will be when n is equal to 3, so that's negative 1 cubed, which is negative 1, over 6 times 3 is 18, plus 2 is 20, times 2 times 3, which is 6 factorial. And 20 times 6 factorial is going to be 14,400. This right here, this term, is smaller than 1 over 1,000. Okay, so if I add up the first 3 terms, these first 3 terms here, that's going to give me an approximation that is accurate out to 3 decimal places at least. Okay, so 1/2 minus 1 over 16 plus 1 over 336 is approximately 0.44044762. Okay, so that gives us an approximation for the value of that integral. Okay, so really, really good problem, like utilizing just about everything that we've talked about in the second half of chapter 11. Okay, and guys, that is it. That is our last formal example in Calc BC. Obviously, we're going to be doing a lot of like AP test prep and stuff, but yeah, we have nothing new to learn. So congratulations on surviving the course. And like I said, I hope you guys like find the mathematics as beautiful and as interesting as I do. I think this stuff is so awesome, and I love that it's saved for the end of the year in this class. Okay, so this should be able to like allow you to work through the free responses that I gave you. Again, like those free responses are not easy questions. Like these types of questions on the AP test are far and away the most difficult. And I'm going to give you guys a good amount of time to practice with this before you are assessed on it. And hopefully in doing a bunch of practice, like free response style questions, you get a much better feel for like what types of questions College Board likes to ask. You guys, as you get more comfortable, should be able to fare a lot better with these types of questions. So hope you guys have a great spring break, and we'll see you all in about a week and a half. All right, take care, everybody. Bye.